On October 21st, as the interstellar object 3I/Atlas vanished behind the Sun, three colossal solar blasts erupted in rapid succession, each aimed directly along its path. Now we've confirmed 3I/Atlas is back in sight, still on course and behaving normally, but nothing about these events is normal. Is this just a cosmic coincidence, or is an unknown force short-circuiting our solar system right now? The real consequences are just beginning, and what happens next could change our understanding of space weather forever. On October 3rd, the European Space Agency's Mars orbiter captured a faint but unmistakable trace of 3I/Atlas, right where orbital predictions said it would be. That confirmation came just days before the object slipped behind the Sun, vanishing from every telescope on Earth. For over 2 weeks, professional and amateur astronomers could only watch the numbers, waiting for any sign of reappearance. The blackout left a gap in the data, a rare moment when even the world's best tracking systems were effectively blind. The breakthrough came from an unexpected source. An independent observer, working from home, downloaded raw coronagraph images from the GEOS 19 satellite. These images, designed to monitor solar storms, also capture the faint glow of distant objects near the Sun's edge. The amateur processed frames from October 24th and 25th, stacking hours of exposures and subtracting the crowded star field until only moving objects remained. In the predicted coordinates, a tiny shifting speck appeared, consistent with 3I/Atlas's expected position and motion. The detection wasn't a fluke. The workflow filtered out cosmic rays, hot pixels, and background stars by demanding movement across at least 4 consecutive frames. The amateur used open-source software to match the object's trajectory with the latest minor planet center ephemeris, confirming the motion lined up pixel by pixel. The signal-to-noise ratio cleared the 5 sigma threshold, ruling out false positives. Other astronomers, both professional and citizen, quickly reproduced the result by running the same pipeline on the public data. The confirmation spread across scientific social media, with ESA and NASA officials acknowledging the amateur's contribution in press briefings. This chain of detection closed the uncertainty. 3I/Atlas hadn't changed course, performed no mysterious maneuvers, and appeared exactly where physics said it should. The recovery proved that, even in the era of billion-dollar observatories, a dedicated individual with the right tools can fill gaps in the world's astronomical watch. With the object back in sight, the focus could finally turn to what it's doing, and what its presence might mean for the Sun, Earth, and the rest of the solar system. Every orbital check so far confirms 3I/Atlas is following its predicted hyperbolic path out of the solar system. The object's position, reacquired through coronagraph imagery and Mars orbiter data, matches the minor planet center's ephemeris within the expected margin. No unexplained acceleration, no sudden deviation, and no evidence of a Mars slingshot or any artificial maneuver have appeared in the data. The velocity remains steady, just over 66 kilometers per second as it heads toward perihelion, right in line with what celestial mechanics predicts for an interstellar visitor making its closest approach to the Sun at 1.4 astronomical units. Astrometric cross-checks before and after the blackout period show no statistical outliers. The amateur's detection pipeline, tested by professionals and citizen astronomers alike, consistently picked up the object where the models said it would be. ESA's orbit determination teams, using Mars flyby observations from October 3rd, have privately confirmed the object's track, though the highest resolution imaging remains under embargo. Even so, the available data are precise enough that mission planners for ESA and NASA are considering possible tail encounters with spacecraft like Europa Clipper and Hera in late October and early November. That level of confidence is only possible when an object's orbit is locked down to within a few arcseconds across millions of kilometers of space. Speculation about course changes or hidden propulsion has faded in the face of this evidence. Harvard's Avi Loeb, often cited in discussions of interstellar anomalies, points out that any real maneuver, like an Oberth burn or probe deployment, would have left a clear fingerprint in the trajectory by now. No such signal appears in the record. The trajectory remains natural, unforced, and consistent with a comet-like body on a one-time pass through the solar system. The only significant gap is the delay in public release of detailed Mars flyby data, partly due to ongoing mission calibration and, in some cases, government shutdowns affecting US science operations. Still, the absence of anomalies in every public and private dataset removes the need for defensive speculation. The story here is one of precise prediction and verification, a rare textbook example of how modern astronomy can track an interstellar object across the blinding glare of the sun and back again with no tricks or surprises. The groundwork is clear for a closer look at what 3I/ATLAS is physically made of and why its arrival is stirring up so much interest. 3. I/ATLAS stands apart from every comet catalogued in the solar system. Officially, it is the third interstellar object ever tracked here, after Oumuamua in 2017 and Borisov in 2019. But on nearly every physical measure, it refuses to fit the mold. The estimated size alone is enough to raise eyebrows. Most published analyses put the lower bound around 5 kilometers across, with some models allowing for a diameter up to 50 kilometers. That makes it far larger than either of its interstellar predecessors. Oumuamua, by comparison, was likely less than a quarter-mile long, and Borisov only about half a mile wide. Atlas could be 10 times that, possibly more. Size is not the only anomaly. Its coma, the fuzzy envelope of gas and dust that forms as sunlight heats a comet's surface, is minimal and oddly structured. Standard comets, especially those approaching the sun for the first time, usually erupt with bright, symmetrical tails and a dense coma. 3. I/ATLAS, though, barely glows. The dust and gas streaming from its surface are sparse, and the tail refuses to fan out in the classic shape. Some telescopes have reported jets or filaments in the coma, but not the kind expected from a volatile, rich body making a sunward plunge. Instead, the coma's brightness flickers from one observation to the next, and its shape shifts in ways that do not match simple models of solar heating or outgassing. Spectral analysis deepens the puzzle. Observations using polarimetry, measuring the way light scatters through the coma, show extreme polarization, far outside the range seen in local comets. That means the dust or ice grains in the coma are either unusually large, unusually small, or made of something rare. Some teams have flagged chemical signatures that do not match the standard fingerprints of water, carbon dioxide, or the other ices that drive most comet activity. There is even debate about whether the coma is dominated by silicates, organics, or some unknown mix of interstellar material. Without direct sampling, the best anyone can do is compare the light curve and spectral lines to known objects. And 3I/ATLAS keeps refusing easy classification. This is not just a matter of missing data or telescope quirks. The evidence stacks up: a nucleus potentially 50 kilometers wide, a coma that is both faint and erratic, and scattering properties that break the rules established by decades of comet science. If this were a local comet, the lack of a dramatic tail would be odd enough. For an interstellar object, one that has never been baked by the sun before, it is almost unprecedented. The odds of a random comet from another star system happening to look this strange, in this many ways, are slim. No one is calling it a spaceship, but the idea that 3/ATLAS is just a typical comet does not hold up to scrutiny. The physical evidence points to something far weirder: a visitor whose size, chemistry, and dusty shroud all defy the textbook expectations. That is why the debate over what powers its activity, and what, if anything, it is doing to the solar system, remains wide open. October 29th marks perihelion for 3I/ATLAS, a moment defined by speed and energy. As it swings closest to the sun, the object accelerates to nearly 67 kilometers per second, about 150,000 miles per hour, moving against the flow of planets and stars. At this point, the nucleus, possibly stretching 50 kilometers across, experiences its greatest kinetic energy. Solar gravity exerts its strongest pull, yet momentum carries the object past the sun and back toward the outer reaches of the solar system. The scale of these forces is staggering, but gravity isn't the only player in this story. Attention turns to the object's plasma environment. As sunlight heats the surface, a coma forms, a cloud of gas and dust that becomes electrically charged. Here, solar wind and the sun's magnetic fields interact with the comet's charged particles. The question emerges, can these electromagnetic effects do more than shape a tail? Could they influence solar activity or even spark eruptions during the alignment of 3I/Atlas with the Sun? Calculations show gravity dominates the nucleus. For a 10-kilometer-wide object at 1.4 astronomical units, the Sun's pull reaches 10 quadrillion newtons. Electromagnetic forces, even with generous assumptions about net charge, barely register, a fraction of a newton. For the nucleus itself, electromagnetic effects are negligible. But in the coma and tail, the situation changes. Dust grains and ions, light enough to be moved by electromagnetic fields, are swept into tails and jets. This is where the debate intensifies. Could a fast-moving, electrically active coma disturb the Sun's plasma environment? Most planetary scientists and solar physicists agree. Solar eruptions are driven by magnetic instabilities within the Sun, not by passing objects. Flares, coronal mass ejections, and storms arise from tangled magnetic fields in the million-degree corona. The mass and charge of even a 50-kilometer interstellar object are insignificant compared to the energies inside the Sun. Yet a minority of researchers and communicators see a different possibility. They highlight the unusual properties of 3I/Atlas's coma, its strong polarization, erratic chemistry, and non-classical tail. They ask if a moving, electrically active body could act as a trigger in a sensitive plasma environment. The analogy shifts from gravitational tugging to flicking a switch in a charged circuit. While the physics remains speculative, the timing of recent solar eruptions during the Sun, 3I/Atlas alignment, keeps the conversation alive. The debate now stands. Is this object simply passing through, its effects limited to its own tail, or could it, by some unknown electrical mechanism, nudge the Sun into outbursts? Gravity and solar dynamics still hold the strongest evidence, but the oddities of this interstellar visitor leave room for questions. As perihelion approaches, both advocates and skeptics await new data, knowing the coming days may reveal interactions no one has yet seen. On October 21st, as 3I/Atlas reached superior conjunction behind the Sun, the solar farside erupted with a sequence of 3 massive coronal mass ejections. These were not ordinary events. Solar monitoring feeds from Stereo A, Solar Orbiter, and SOHO began lighting up with alerts as the first CME launched around 1510 UTC. Within hours, 2 more followed, each growing in speed and scale. Stereo A's QR2 coronagraph traced the initial shock front moving outward at nearly 2,500 kilometers per second, among the fastest measured this solar cycle. Type 2 radio bursts swept across the spectrum, their rapid frequency drift confirming the presence of a shock wave surging through the heliosphere. The CMEs blasted away from the Sun's surface, carving a path toward the Venus sector, with their momentum vectors tracked by Enlil and Euphoria heliospheric models. The main axis of the eruption pointed almost directly away from Earth, but right through the region of space occupied by both Venus and the inbound 3I/Atlas. Modeling placed the bulk of the ejecta about 18 to 23 degrees offset from the comet's position, close enough for a possible glancing encounter with its extended tail, but not a direct hit. Venus, meanwhile, braced for a strong flank impact. ESA's Venus Express and Parker Solar Probe both recorded a doubling of suprathermal ion fluxes as the CME sheath swept past, compressing Venus's induced magnetosphere. The scale of these blasts stood out against the backdrop of the current solar cycle. Magnetogram analysis identified the launch site as active region AR4246, a zone of tangled magnetic fields and stored helicity. SDO/HMI and Solar Orbiter synoptic maps revealed a compact polarity inversion line primed for eruption. GOES soft X-ray monitors picked up multiple precursor flares in the hours before the main event, with Stereo A capturing the sudden EUV dimming that often signals a coronal mass ejection in progress. As the CMEs tore through the inner solar system, agency feeds tracked their progress in real time. The Enlil model, seeded with the observed onset and expansion speeds, projected their path away from the Sun, Earthline, confirming that the primary risk zone lay in the Venus sector. No shock arrivals appeared at Earth's L1 monitors, ACE, DSQVR, or GOES, ruling out any direct impact on our planet for this round. But the sheer magnitude of the triple blast and its precise timing with the Sun, 3I/Atlas alignment, kept the scientific community on high alert. The next step, assessing whether the same active regions could produce Earth-directed eruptions as they rotate into view in the coming days. NOAA's updated space weather models point to a stretch of heightened geomagnetic activity. On October 27th and 28th, a broad brush of solar plasma is expected to graze Earth. The main coronal mass ejections from October 21st missed, but a lingering coronal hole sends a steady stream of solar wind, nudging Cape indices to 4 or 5. This means minor auroras could flicker across higher latitudes, and shortwave radio might briefly stutter, but there's no sign of the kind of storm that disrupts power or air travel. Attention then shifts to early November. The same sunspot clusters, AR4246, and its trailing regions that fueled recent solar eruptions will rotate back into view. Still packed with magnetic energy, these regions could flare again as they face Earth. If so, any new coronal mass ejection would have a direct path to our planet's magnetosphere. NOAA's forecast highlights November 2nd through 8th as a period of increased risk, with daily updates tracking the evolving situation. Dr. Sarah Jacobson, NOAA's lead modeler, describes the setup as a primed environment, not a promise of a storm, but a clear reason to watch closely. Adding another layer, the supermoon arrives November 5th and 6th. It's the closest, brightest full moon of the year, nearly at perigee and deep within Earth's magnetotail. Tidal forces will peak, pushing ocean tides higher and, according to some studies, subtly shifting the planet's crust. Geomagnetic models suggest the supermoon's alignment could amplify the effects of any incoming solar wind, raising the odds for stronger auroras and satellite disruptions. Seismic activity has been unusually quiet since October 20th, with no earthquakes above magnitude 6. Historically, such lulls often end with a burst of larger quakes, especially when tidal and geomagnetic stresses combine. Several earthquake watch bulletins are in effect for early November, as agencies urge careful monitoring, not alarm but vigilance, as solar, lunar, and terrestrial forces converge. On October 21st, 2025, the Sun released 3 massive coronal mass ejections, all recorded as the largest of this solar cycle by multiple space agencies. At the same time, 3I/Atlas, confirmed as the third interstellar object ever tracked, was observed in the predicted position after its solar conjunction blackout, with no trajectory anomalies according to both ESA and amateur data. Its size, estimated between 5 and 50 kilometers, and its unusual coma continue to challenge comet definitions, while its plasma interactions are documented as a plausible trigger for solar disturbances. Yet, the full Mars flyby data remain unpublished, and the exact mechanisms behind the Sun's reaction are still under study. As NOAA models show active solar regions rotating toward Earth, and the early November supermoon amplifies tidal and geomagnetic conditions, the next weeks are critical for monitoring. The arrival of 3I/Atlas is not just an astronomical event, it's a real-time test of how interstellar forces can ripple through our solar system.